pseudoscientists to scientists and technologists, and where we can really really think about modeling real life situations, and we are fulfilling what are the requirements associated with that, right? So in that direction, whatever discussions we had previously, we are going to last 2-3 things, we are going to really address. So one of the main things that we are going to address is what we did not address until this point is how exactly pressure comes into picture. What is the distinction between pressure and stress? How exactly we connect force to the stress? And then, how exactly we get the symmetry of the stress tensor through the angular momentum balance. And then, how Newtonian, non-Newtonian, and Hookean domain operates. Now, if we complete all these aspects one by one, so things will be under control in terms of your implications, your utilization of the theories for the all the small scale processes. So whenever I am discussing some theory, and I'll always keep in mind as a very simple geometry that there is a microfluidic channel like your blood vessel, and then there is a fluid like your blood, a real fluid like your blood, okay, like serum or like sputum or like sweat, any real fluid that is flowing through that channel. That's what ultimately you have to really model, and ultimately you have to really get information about that system without doing any experiment. That's the overall target of developing the conceptual computational models. So let me just share my screen. My screen is visible to all of you, right? Somebody confirms?
Yes, sir.
Yeah. Yeah. So now I think with all the basics, backgrounds, whatever we have discussed, you are now more or less comfortable with this notation that, V is suppose V is the velocity, N is the normal. Say, suppose you have a surface which is ds, where N is the normal in this direction, which need not match with the direction of the velocity. But if you really want to calculate the flux, then what you need to do, you have to write V dot N ds. Correct? This is the volumetric flux. And you understand that since this is written as a surface integral, that means, you can write with 2 integrals or you can write with like this. But at the end of the day, what you are talking about, if there is a circle like this, you are actually taking care of the entire ds, ds tends to infinity. Correct? So in that process, you are calculating you are accumulating from each and every phase what is the flux, and you are adding it. So essentially, for a line, you are in a 2D domain, and for an area, you are in a 3D domain. So you are much more realistic in terms of your computational effort. Now, if you multiply this volume flux parameter with density, you will get the mass flux. You will just see I have multiplied this with density. Hello, can I give you a call little later? Yeah, I'm inside a class. Yeah. Now, if I multiply this with rho and v, that becomes a momentum flux. If I multiply this by half rho v square, that becomes kinetic energy flux. So you can essentially see that if this is an arbitrary parameter, correct? So flux of these arbitrary parameters, this can be intensive, okay, and that can be an intensive parameter. So you can really multiply by this. Now this is a surface integral. If you convert into a volume integral through a divergence, Gauss's divergence theorem, you are going to get like this. These are all elementary things now. Whatever fundamentals that we have discussed, you should really breeze through all these things without much of hassle. So just to tell you that, this particular framework makes you ready. The whole bunch of things you can do without much of hassle. So now all these parameters are, that they are important. Let's say suppose there is a fluid that is flowing through a channel. You need to measure what is the volume of the fluid, volume rate of the fluid, at what time that volume is coming, then mass rate of the fluid. So all these things that you know. What you do not know is how to connect these parameters to the force. And that's what we attempted in last two classes, to connect how exactly the force and these parameters like distance, time, space, volume, velocity, all how these parameters, they are getting integrated into the force framework. In next 10 slides, we are going to now summarize it to a kind of very generic framework, right? We are going to really summarize the whole thing that we have done up to this point into a few quick slides, telling that, say, if you have an arbitrary surface like this, which has a surface like delta S, and on which you have put an arbitrary force that is delta F, with the surface normal as n. So we define a vector called T, which is the traction vector, which is del F by del S. So T is like any other vector. So this traction vector can be any other vector. So if this is the traction vector, it has three components. Say suppose T1, T2, and T3. Okay, so traction vector is a vector, which has a suppose T1, say suppose T2, say suppose T3. These are the three arbitrary directions the force can be applied on a surface. And we define del F by rho del V as the body force. So this is the measure of my surface force, and this is the measure of my body force. So you can see that, say, if this is a cube, if this x1, x2, x3 are normals, these traction vectors are defined in three arbitrary directions, which is the most generic way of representing things. This is very, very important because this is now going to give you the clue how force is correlated. See, the confusion that I created for the calculation, say suppose pressure you are thinking about, right? Pressure, you are saying that force per unit area. And then you are saying stress. Stress is also a force per unit area. Now question is that pressure is a scalar. Okay, but force stress is a tensor. How is that so? Why is that so? What is the reason? Both are force per unit area. So fundamentally, we are attacking the problem that we first define a traction vector. Hello?
Yes, sir.
Sorry, there was some issue with the internet. Am I audible now?
Yes, sir.
Yeah. So we define a most generic possible way the force, how the force is acting on a surface area as the traction vector. Okay, and most generic way we define B as the body force, and now see how we progress about the traction and the body force in correlating the surface and the body force. Then what we say, we come up with a statement that this traction vector is nothing but is just a dot product between the normal and a stress. This particular stress is called the Cauchy stress. So what I say that first I arbitrarily put up a coordinate system, say suppose X, Y, and Z. So suppose this is X, Y, and Z. Okay, and there, based on the areas that are there, the defined areas there. What is this plane? Can somebody tell me what is this plane can be called? This particular plane. What is this plane? Say if this is X, Y, Z, this particular plane is called which plane?
YZ plane.
Very good. This is Y, this is Z, right? So this is a YZ plane. So I have already defined the plane which is perpendicular to X, right? So if X is this direction, YZ is the plane that is perpendicular to that, right? Similarly, what is this plane? What is this particular plane? Sorry. What is this particular plane?
XY plane.
This is an XY plane, but it is perpendicular to Z, right? And what is this? What is this plane? What is about this plane? That is at the top of this cube. This is a XZ plane, right? Which is perpendicular to Y. So what we did, we first defined the planes, and that on that plane, what we have defined the directions of the stresses also. So this is T11, this is T12, this is T13. This is the normal stress, and these are the tangential stresses. So like T2 to T1. Now, if I assemble them into a tensorial matrix, it will come out to be like this. Now, what is N1? N1 is the normal. N1 is the normal in this direction. N2 is the normal in this direction, and N3 is the normal in this direction, right? Now I say that, say the distraction vector is nothing but N dot T. That means whatever the stresses that has manifested in all this direction, if you just sum up with N1, N2, and N3, it is going to give you the if you are going to project to N1, N2, and N3, it is going to give you the traction vector. Right? Let us look at it a little bit more. So what I do now, I just play around with this parameter a little bit more. So I put a kind of X, this is Y, and this is Z. Okay, forget about this for the time being. Focus on this first. How do I draw a tetrahedron here? Can anybody guide me? So suppose there is a point in which this is intersecting. There is a point here it is intersecting, and there is a point here it is intersecting. How do I draw a tetrahedron?
We connect all the 3
points, right? So a tetrahedron has how many faces? One is this face,
4.
One is this face, one is this face, and one is this cover face, right? So essentially you have 4 triangles, correct? So now this tetrahedron, through this tetrahedron, what I do, I define an arbitrary point here, and this is my origin. And I say that through this surface, there is this particular place, this particular point, through which there is some force that I'm applying. Okay, there's some force that I'm applying. Okay, even before applying the force, what I say that if this is the surface, there is an arbitrary direction through which this is the normal, which is through normal to this particular surface, which is the capping surface at the top. I just define that to be the normal. Right? So now you look at this particular. Geometry. So x1 is essentially x, x3 is essentially z, and x2 is y, and you have this tetrahedron on top of that. Now that tetrahedron has this particular distance between these two that you define as the height of the tetrahedron to be h, this particular point as n, right? Now this surface at the top is delta S. So you can really resolve, this delta S into 3 different components. One is delta S1, this one, delta S2, this one, delta S3 is that one. Correct? So delta S is nothing but delta S1I, delta S2. Here it is delta S1 and K, delta S2 in this direction. That means it is J, and delta S3 I. Right? So one in the x direction, one in the y direction, one in the z direction. correct? Now, if this is the n, if this is the normal, which is piercing through this capped surface, capped triangular surface, this n can also be resolved as n1, n2, and n3. Now, if you look at n1, you can say that n1 is equal to cos AON, AON, AON. Okay. So from the geometric rule, we can say that n1 equal to cos AON, n2 equal to cos BON, and n3 equal to cos CON. So AON, CON, and BON, just by geometric arguments. And then what you can write, H is equal to OA, sorry, OA into N1, OB into N2, OB into N2, and OC into N3. So H is nothing but, this is again coming from the geometrical argument that OA, the N1 into OA is my H, N2 into OB is my H, and N3 into OC is my H. So, I can really define two geometrical parameters. And then if I want to calculate delta V of this tetrahedron, what should I do? Is by standard formula 1/3 of H into delta S, which will be 1/3 of, now H has OA into N1, that is OA into delta S1. Then 1/3 of OB into delta S2, and 1/3, just I'm using this relationship in order to make that, which gives me a very interesting correlation, delta S1 equal to delta SN1, delta S2 equal to delta SN2, which is obvious, right? Delta S equal to delta SN1. So, delta S has three components, delta S1, delta S2, delta S3, in which direction? N1, N2, and N3, which we were debating in the beginning. Just by kinematic argument. I am not doing any force balance. Anything that I have done in this particular slide is what? This is a kinematic analysis. So everything is coming, whatever arguments I am giving here, that is coming from what? That is coming from the geometrical argument. Now you see, I go towards now I bring in the dynamical aspects associated with the whole thing. So this here I am bringing in the dynamics part, okay, where, I'm bringing in what? I'm bringing in Newton's law of motion, total momentum to total force. So in that process, now you again look at the tetrahedron. So suppose on the surface, you have a traction vector which is acting on delta S. So that can be resolved into, say, suppose T2 is delta S2, T1 delta S1, and T3 delta S3. Whereas from the center of gravity of this particular tetrahedron, you have rho B delta V that is acting as a body force. So how do I make sure that the Newton's law is acting? So it is saying that rate of change of momentum rho delta V dV by dt is equal to what? Is equal to all the surface forces acting together, all the body forces. So this is the body force. T delta S is in this phase, and in all these phases, this is T1 delta S1, T2 delta S2, T3 delta S3. So if I just divide this with delta V, so I end up getting this. And then what I do, I put H tends to 0. Why am I putting H tends to 0? Because if I put H tends to 0, delta V becomes 0. Then I only accumulate all the surface tractions together, which gives me a very interesting correlation that T is nothing but Tn1, Tn2, T. Like here I did what delta S is what? Delta S1 N1, delta S2 N2, and delta S3. I mean, delta S1, delta S2, and delta S3 are nothing but the components of delta S in three different directions. So similarly here I get T is nothing but it's a combination of Tn1, Tn2, Tn3, like T, K, N, K, which I summarize as what? So traction is nothing but N dot T. This is nothing but what? This is nothing but N dot T. So this TK, what is this TK? T1, T2, T3. It is essentially the stress which is acting perpendicular to the plane of the coordinates. So here what we were arguing, here what we were arguing, perpendicular to the plane that I have defined. So this particular plane, what is this plane here? Sorry. What is this plane here? Anybody tell me what is this plane? Say suppose this is X. Suppose this is X, this is X, this is Y, and this is Z, right?
YZ plane, sir.
So this is a YZ plane. What is this plane? What is this plane?
X5 plane.
This is an XY plane. What is this plane? This is an
Z
XZ plane, right? So, so now perpendicular to that, you are resolving this to be say T1, T2, T3. So these are all. So how from, so this is what is my, for an arbitrary plane, this is what is my traction vector that is acting on delta S. Whereas, when I'm resolving it to the normal, to the plane that I have, reference frame is mine, reference frame nobody else. This is somebody is, pulling the car, that person will not be worried where is the reference frame, is that person is just, putting the force and pulling it. Now, if you really want to know what is that, so what you have to do, you have to resolve it in the reference frame that you have put in, and that you resolve in 3 different directions. And the formula that comes out in generic for a given arbitrary geometry, applying the Newton's second law with limit, there is no volume that is existing, that this traction is nothing but, just vector addition of the 3 from the combination, and that comes out to be what? That comes out to be the formula, like T1 is this, T2 is this, T3 is this. So like, Ti is this. That means normal to, if you have a Cauchy stress, which is like this, if you take a divergence, if you take a dot product with M, you are going to get what? You are going to get the traction vector. Why traction vector is important? Because traction vector is correlated to the force and its arbitrary force and its arbitrary direction where it is applied. Right? Whereas stress is like, I am now, once I am aware of the force, I am now bringing it to the planes where I can make the analysis, and around that planes, I am just, resolving that stress in order to set up an equation so that ultimately from any arbitrary surface, I am able to calculate the force. Any questions up to this point? Any questions? Anybody has any question? You have understood, right? Great. Now, when you have this Cauchy stress, so this is not the most fundamental property. What is the most fundamental property? The most fundamental property is your traction vector. This is your most fundamental property. In order to really calculate this force per unit area, you are creating a framework like this, where by definition from traction, while you are transforming the traction vector into your reference frame, there you obtain the stress tensor, which is the basis of your calculation. And from the stress tensor, what you do, you first take the determinant of the stress tensor. So your stress tensor is like this. And then what you do, you take the determinant, and determinant minus lambda. What am I attempting here? Can anybody tell me? What is this thing called? When I take a matrix and when I just,
eigenvalue.
What is an eigenvalue? Anybody has any idea?
So when we,
what is the eigenvalue of a matrix?
So when we linearly transform a vector with a matrix, and if the vector does not change its direction, it's only a scales in magnitude, then such a vector is supposed to be an
all of you should submit what is the eigenvalue of a matrix. Okay. All of you should submit. I know that there is a huge confusion in your head in terms of what is an eigenvalue. Right? So all of you first should know what is a matrix, right? So suppose when you put up a matrix, why are you putting forward that matrix? And then why are you trying to determine the eigenvalue, right? Let me give you a physical hint for that. So suppose you have a matrix, right? And you want to know whether the matrix is a diagonally dominant matrix or not. So suppose you have a matrix which is like this. 1, 0, 0, 0, 1, 0, 0, 0, 1, right? This is called an identity matrix, right? Whether it's a diagonally dominant or not. Yes, no. Did you get my question? Hello.
So what do you mean by diagonally dominant?
Do you know what is a diagonally dominant matrix?
I know what is a diagonalizable matrix, but
Diagonally dominant matrix means, say suppose you have a matrix which is, say this is T11, T12, T13, right? T21, T22, T23, right? T31, T32, T33, right? In this one, say when you take a matrix, what are the utility of a matrix? Why you learn matrix determinants and all these things? What is the purpose of learning? Can you give me one application of learning matrices? Why are you learning this mathematics?
so matrices can be used to solve linear equations.
Like linear algebraic equation, you have simultaneous equations, right? And say suppose you have x1, x2, x3, x4, x5, x6, x7 to xn. You have a algebraic equation, set of algebraic equation. You have an n by n matrix, and you want to get the solution for x1, x2, x3, x4, x5, x6 till xn. So what you do, you put a matrix form, right? And then what you do, you use Gauss's elimination method, right? So
Yes,
what
sir.
you do, you replace, one by one. In that process, what you do, you take the coefficient matrix, and from the coefficient matrix, you try and invert the matrix in order to get what? In order to get the solution associated with x1, x2, x3, x4, xn, right? Now, when you do that, what you need to know when you are trying to go for a matrix inversion, or when you are taking a coefficient matrix, what you need to do, you need to really solve the matrix, the coefficient matrix and all, everything. You need to solve the matrix. Now, say suppose a 3 by 3 matrix, you really know how to solve this matrix, how to come up with the numbers and all. Suppose if it is an n by n matrix and n tends to, say suppose 1 million. So it has to be done by a computer, correct? So generally you don't use Gauss elimination. What you do, you use Gauss-Seidel method. What is a Gauss-Seidel method? You assume x1, x2, x3, x4, xn. You assume a solution, say 1, 2, 3, 4 arbitrarily. You put into the matrix, you calculate the error, and then what you do, you minimize the error in an iterative process to make sure that you have a solution for x1, x2, x3, x4, x5, x6 till xn. Now this you do using a computer programming, correct? Now, when you are solving, when you are really working with the matrices, and when you are really solving this sort of algebraic equations, what you need to really solve the matrix. You need to really work with the matrix. So in that, what you need to know what are the items in the matrix. Say suppose you have an equation which is say x1 plus x9, okay, plus x11, okay, plus x331 equal to 0 in 1,000 x1, x2, x3, x4, xn. So in that process, these are the coefficients which are 1 in the matrix, and other coefficients, say from 0 to 1,000 variables, those coefficients are 0. In that process, you take the coefficient matrix out, right? So when you take a coefficient matrix out, if you have most of the numbers which are populated, okay, in the diagonal direction, okay, let me just show you one example. It will be easier for you. So if you really have matrices where, like, the heavy numbers are all near the diagonal. Okay, these are called typically, like, the diagonally dominant matrices. Why? Because this type of diagonalization of the matrix, help you in iteratively converging much faster. When you have n by n, 2000 by 2000, say suppose if you look at this particular matrix, right? So here what you will find, this particular matrix, right? I think it is visible to everybody, right? My console is visible to everybody, right?
Yes.
So when you are solving a set of linear equation, you may see that the diagonal portion of the matrix is populated, whereas these portions away from diagonalization, you may see that these are populated with 0. This is a typical, like typical finite difference when you are solving iteratively finite difference method. This type of matrices. This is about 3, 3, 6, 9, 9 by 9 matrix, right? So you will get about 900 by 900 or 9,000 by 9,000 or 9 lakh by 9 lakh or 9 million by 9 million. But then you will find that those are all diagonally dominant matrices, right? So this sort of matrices, it becomes much easier to really solve these matrices which are diagonally dominant in nature, right? Now what I wanted to say towards this, that say suppose you have, now I think you are clear what is a diagonally dominant matrix, right? So now I again put the identity matrix like this, and I ask back the question with the examples that I have given for diagonally dominant matrix, whether this is a diagonally dominant matrix or not. Yes or no?
Yes, sir, it is.
It is a diagonally dominant matrix, right? But this you can really decide from looking at the diagonal. I mean, whatever examples I have shown you, those you can really decide just looking at the diagonal, right? But the previous example that I had given, say suppose this one. Can you decide this just looking at this? Can you decide that whether it is a diagonally dominant or not? So just looking at this, can you decide it is a diagonally dominant or not? Most of the times you will be able to say, suppose this is 3 minus 3, 4. You may say that, yeah, this is a diagonally dominant matrix. But most of the matrices, if you look at them suddenly, like say, suppose if you look at this one, and if these are not 0, you will not be able to decide. Correct? Diagonal dominance is not decided just by looking at it and say, suppose if I give you this one, you do not know whether it's a diagonally dominant or not. How do you do that? What you do, you get the eigenvalue of that. Right? How do you get the eigenvalue? And I will immediately convince you why it is so. So what you do, you take the matrix, you put minus lambda to the diagonals, and then you take the determinant to be 0. So what type of algebraic equation is this? Anybody tells me in terms of lambda?
Cubic equations.
It's a cubic equation, right? Everybody is clear because minus lambda, there'll be lambda cube. So essentially the equation will look like this: lambda cube minus it lambda square, 2t lambda and 3t, right? 1t lambda square, 2t lambda, 3t. If you solve it, you get 3 values of lambda. So essentially you get 3 roots of lambda from here, which are called the invariants for this particular matrix. Right? What is invariant? That means, the numbers that you will get out of it, this 1, 2, and 3, is first invariant, second invariant, and third invariant. The numbers that you will get for these lambda values, these numbers will remain constant. It will be irrespective of your coordinate system. Correct? Invariant means it's a real constant. Those numbers are real constant. When you do Pascal's law at a particular, say when you're looking for a hydrostatic heat at a particular point, when you are looking at the pressure at different directions, pressure remains to be the same in all different direction at a particular point. That means even if you rotate, it is frame invariant. Suppose you are making nimbu pani, right? So you have water, you have sugar, and then you are mixing it, right? Now, when you are mixing it, Earth is also rotating. So that means there is a motion, Earth is moving, rotating, right? But when you are mixing it, most probably in this mixing, the rotation of Earth, the movement of Earth has very less influence. It is the mixing that you are doing that has the most influential thing, right? So this dynamics is not dependent on the movement of the earth. So there is an invariance associated with this dynamics. So most of the physical constants that you identify, whatever constants you say, no, they are not real constants. Okay, what are the real constants? Real constants are the variables that originate as invariants from the mathematical analysis. Those are only called like the velocity of light. Okay, that is what is an invariant. There are very few parameters in this world which are really frame independent. Which are really independent of the framework that you are putting in. If you are changing the framework, and with that, if the property changes, that particular thing is not constant. Right? So even if we use them as a proportionality constant, that most of the time they're not having the property of frame invariance. If you want to have a frame invariance, how do you do that? You first get the matrix, the determinant, the eigenvalue. Now you see the first eigenvalue represents what? T11, T22, T33. That means TKK. That means stress of this stress TR. TR means stress of T. Is the addition of all the dominant. So if you take the first invariant, so you are getting the first eigenvalue lambda. You know, this corresponds to the first lambda. The roots of lambda, IT gives you what? IT gives you, lambda has 3 different roots, right? Lambda is giving you, from lambda, you are getting lambda 1, lambda 2, and lambda 3, right? You are getting 3 different roots from lambda 1, lambda 2, and lambda 3. And from there, you are getting 3 invariants. One is called IT, which is the trace of T, I2T. So this is the diagonalization factor. This I2 is giving you the, apart from diagonalization, whatever other factors are there, the trace factor here is there. Right? And then third is giving you the determinant of T. Right? What is the utility of this? You can straight away see that. Now I define the thermodynamic pressure P as what? 1/3 of T11, T22, and T33, which is an invariant. This is an invariant. According to this analysis, this IP is an invariant, and 1/3 of that. Why do I do 1/3? I take an average. 1, 2, 3. And that I define 1/3 of TKK I define as the thermodynamic pressure. Right? And then what I do, I define the Cauchy stress matrix. I divide into 2 parts. One part is with the invariant part, which is my thermodynamic pressure. So this is also force per unit area. And I define this as the deviator matrix, which is also force per unit area, where I exclude this part. So as I said that previously, that sigma is equal to what? Small p, that there's a notation confusion is there. Just, take care of that. Sigma is what? Sigma is pi, where I is the identity matrix, plus what? Plus tau, minus pi plus tau. So what is tau? Tau is the deviatoric stress. What is sigma? Sigma is the total stress. What is P? P is the thermodynamic pressure. From the total stress, which is the Cauchy stress. This is the Cauchy stress. This is the Cauchy stress, right? If you take the thermodynamic pressure out of the whole situation, you get the this is called the deviatoric stress. Okay. Now deviatoric stress has 2 components. One is the normal component, okay, which is what? Tau xx, tau yy, tau zz. So these are called the normal deviatoric stresses, and the one that is sitting in the around the diagonal are called the tangential deviatoric stresses. Any question up to this point? Is it clear? Is it clear?
So is there any proof like that finding the eigenvalue only would give us whether it is a diagonally dominant or not? Like how did one figure out that?
So suppose this number is very high. So I find out this IT to be very high, right? So suppose 10,000. Say when there is a diagonally dominant matrix, no. So suppose you evaluate for identity matrix only. Correct. Then you evaluate these parameters. So you will find that if you find the first invariant and second invariant, you will find that for a diagonally dominant or a kind of for a matrix which is not non-dominant diagonal, these numbers will give you the clue.
Okay,
Whether
sir.
there are zeros, whether there are ones, or whether there are thousands. So suppose I have a matrix which is say suppose I have a matrix which is suppose 10 to the power 10, 0, 10 to the power minus 10, say suppose 5. Correct? I have another matrix. I write another matrix which is say suppose 0, 10 to the power minus 10, okay, 10 to the power minus 100, 1. Correct? So here, if I take the roots, what do you expect to happen? What do you expect to happen in these two matrices? Is it a diagonally dominant?
Yes, sir.
So in this case, you will see this will be higher. Okay. Akshay, I'm in a class. Okay. So this one is also a diagonally dominant. Yes, no. Hello.
Yes, sir. This is also diagonally dominant.
Yes,
So
sir.
now you see that. How do you identify that? How do you know that? You identify the eigenvalues that is going to tell you that whether this will be diagonally dominant or non-dominant. Okay. In a say when you look at the eigenvalues, no, physically, it's a representation. Say essentially a matrix is a vector, right? It's essentially second order tensor, right? But you also call that as a vector. Why do you call it as a vector? Because you are dealing with lot of parameters which are, say, this has a correlation with this and this, fine, in terms of direction, but these are all independent properties in independent directions, right? Yes.
Yes, sir.
Now say suppose I want to know whether this particular matrix is heavily biased towards X. I mean, taking all the points, whether it is heavily biased towards X or heavily biased towards Y or heavily biased towards Z, or all equally distributed. Right? So when you evaluate the eigenvalue of a matrix, those numbers, with the first root, second root, and third root, those numbers that you get, that gives you an idea about the properties of this matrix. Okay, it's a scalar that you obtain. See, it is very difficult for me from here to I can individually understand what is the individual points that we have already deciphered, like what are the individual components here through this Cauchy tetrahedron and all. We are now comfortable. See, this is what is my T11, T12, all these collections are coming. I'm now very much comfortable in getting these Cauchy stresses. But what I'm not very comfortable that what does this particular thing is collectively telling me? Yes, that's not I am comfortable with. What is it collectively telling me? That's where we are now focusing. What is it collectively telling me? Am I audible to all of you?
Yes,
Sir,
sir.
that collective representation is given by eigenvalue.
First is with the eigenvalue, I separate out the pressure, which is the invariant part. Okay, is it clear? Like, from the first invariant, I have figured out that the diagonal part, and from there I separated out the pressure. Is it clear?
Yes, sir.
From the second invariant, I get what? I get about the mixture part. I'm not getting into that first. But when I define that way, I differentiate between the one that is invariant and the one that is varying. As I am changing things in the system, as I am putting force, I am expecting that all these stresses are going to change. This is not going to change. This will be a fundamental property of the system. This I have identified from what? I have identified from the stress tensor and its eigenvalue. This scalar has been identified from what? When I did an eigenvalue analysis, from there I have found out the invariant, and from there I have identified this property. Is that clear? So pressure,
yes, sir.
Pressure is a scalar which is correlated to the eigenvalue of the Cauchy stress, right? The first invariant of the Cauchy stress, right? And that invariant actually helps me in understanding that when I could have put force, what is not going to change in the system in terms of the material, but what is going to change in terms of the material in the system. And this is the origin of the Hooke's law. So first I remove the pressure out, and whatever is the deviatoric stress is there, from there I jump out to go for the Hooke's law or the Newton's law of viscosity. Because that part will be dependent on, that part will not be frame invariant. That part will change as the dynamics is changing. Clear?
Yes, sir.
So I have a very simple definition of body forces, which is rho b dv, and then you know that B is bkik. So these things you people are comfortable. I'm sorry. And I have a traction vector t dot ds. Again, I put it like this. So this is a volume integral. This is a surface integral. So body forces, surface forces. How do I go for a volumetric analysis? This you just numerically take the volume integral, or you analytically you can solve it, no issues. Then you have the total parameter. So there is a shift from your previous analysis where you were doing one-dimensional things. Now you are into the three-dimensional things. Now next come the angular momentum balance. Up to this point, we were only considering the linear momentum. Correct? How do I do angular momentum? So I define an arbitrary point P here. This is my differential, this is my control volume. Correct? So in that control volume, which is dV, I have body force which is working in this, say X, Y, Z, right? Now in that, what I do, I give a rotation, I give a couple, I give a moment. So what will be the moment? Say suppose if B is the body force, here we have defined what is the surface force and what is the body force. Now, if I really want to know the moment of it, what should I do? P is the position vector. With that, whatever is the position vector of this, I take a cross product associated with that, right? Is that clear to everybody? If P is the position vector, see here, if this is the reference frame, where I want to give a couple, okay, where do I want to give a moment, right? Now in that moment, see M is the moment of a force about a point, and F is the surface body force. So M is what? Position vector into F, surface or body force, okay? So if it is B, it will be P cross B. If it is T, it is P cross T. And T is again connected to traction, that is the Cauchy stress, and B is again connected to B1, B2, B3, right? So now if I give P cross B, you can see that, what is P cross B? Epsilon RMN XM, position vector is XI, X1, X2, X3, BN, B1, B2, B3, rho D. Similarly, P cross T will be what? Epsilon RMN XM TN. So XM is nothing but X1, X2, X3, the position vector with respect to the origin. Is that clear, these two things? Now, what is my momentum balance? Angular momentum balance. Very simple. So position vector R cross T ds, this is for the surface force, R cross rho B dV, this is for the body force, and then rate of change of angular momentum. Again, this R cross rho V d dt dV. Is that clear? Is that clear like a daylight for you? So I am starting with the Newton's second law, and then I am with respect to the position vector where things are happening for the control volume. where the position vector is r, I am just taking a cross product associated with that. Right? Is that clear? Is it scary or is it now looking very comfortable? Because I think TDS, rho b dv, and ddt of rho b dv you have already done. This is nothing but your Navier-Stokes equation, right? I'm just taking a couple with respect to r everywhere. Right. Now, if that is so, then what can I write? R cross T ds, epsilon Rmn, xm Tn ds. You have done this so many times. R cross rho b is epsilon Rmn, xm Bn rho dv. And R cross rho b, epsilon Rmn, xm rho Vn. V is the vector here, velocity vector dv. So I just keep m and n together. Okay. Then what I do? I take this epsilon Rmn out. And then this I convert to what? This I convert to surface integral to volume integral. I just apply this. This V a rho a Vj Nj ds to rho a Vj ds. So I just consider that everything has been expressed. This I convert to the divergence theorem. So this becomes what? In terms of Cauchy stress, this becomes divergence of T. And that divergence of T is written like this. So epsilon Rm, this part comes out to be like this. Whereas epsilon Rm, if you take out, this part comes out to be like xm rho Bn, and then you have dv. Whereas in this situation, d dt I take inside. So epsilon Rmn, correct? d dt of xm Bn rho v. So this becomes the summary of my what? Summary of my angular momentum balance. Okay. Now see what happens. Now, let me just take this because otherwise it will be a bit tricky. I'll delete this later. So let me just put this part. I think it's visible to you, right?
Yes.
So left hand side epsilon Rmn xm. I take xm out. Del T Jn by del xj. Okay. This another part xm will go here. I will explain to you. But first, this xm is out. This part is here, and then xm rho b Jn is there. Sorry, there was another network cut. So my slides are visible, right?
Yes.
Yeah. So now you see, see this xm, when I take del xm by del xj, if I take tjn out, which is the case here, right? So del xm by del xj, what should be that? Anybody has any idea?
So delta mj.
Delta mj, everybody can see it. It will be delta mj. Right? How come? X1, X2, X3. This is XYZ. Bottom also XYZ. Now, if you take a partial derivatives, only X, Y, Y, Z, Z are going to survive, right? Because it's a partial derivative, all the cross terms will not survive. So you have delta mj into tjn here, correct? On the other hand, when you take xm out, you have rho bxm and del tjn by del xm. So this is pretty much straightforward with the permutation symbol is outside. Let us look at the right hand side. Epsilon Rmn. What is d dt of xm?
Vm.
So you can see Vm, one term. When you are leaving this Vn outside. And then you have what? Xm dVn by dt rho. Okay? So all terms are clarified here, right? Any confusion? All terms are clarified here, right? So now what you do, say suppose you write epsilon Rmn Vm Vn. What will be this term? Can anybody tell me? Epsilon Rmn Vm Vn. So you can think about 1, 1, 1, 2, 2, 2, 3, 3, 3. These are anyway 0, right? So V1, V1, V2, V2, V3, V3. These are anyway 0. 1, 2, 2, 2, 1, 1, 3, 1, 1. These are all 0. Only one which are 1, 2, 3, 3, 2, 1, right? So what is 1, 2, 3? Here epsilon Rmn, where Rmn is equal to epsilon 1, 2, 3, right? What should be my Vm?
V2 into V3.
V2, V3, right? And what will be my, say suppose you have another, you will have what? Say suppose 3, 2, 1, right? In that case, what will be the, I mean, you have all the combinations, correct? When you have 1, 2, 3, you also have the 3, 2, 1, correct? In that case, what will happen to this?
V2 into V1.
No, sorry. What I have to write is 1, 3, 2.
Yes, sir.
So what will happen to this?
V3 into V2.
Same thing, but what will be the difference between these two? This will be plus.
This will be minus.
Minus.
So it will cancel out.
So you will find, one assignment, just do it. If you just expand it to a summation, you will find this will become 0. Why? Because the pairs will come out like this. Okay, so suppose you take epsilon 3 to 1, right? So in this case, this will be V2, V1, correct? Now, if I take epsilon 3, 1, 2, right? So then this will be V1, V2, but 3, 2, 1, this is non-cyclic, but 3, 1, 2 is cyclic. So this will be minus, this will be plus, so these two will be cancelling out. These two will be cancelling out. In that process, if you take this term, this will be 0. Okay. Now, if you take tau delta mj tau jn, delta mj tau jn, that will be tmn. This will be tmn. Okay, so this term will be tmn. Okay, now this is nothing but the linear momentum equation. So this part is nothing but the linear momentum equation. This part and this part combines to the linear momentum equation. So this is 0. So ultimately, if this is 0, if this is equal to this, so what will happen to this? Tmn epsilon Rmn Tmn equal to 0. You come out to be this. First you come out to be this for volume integral, and then you come out to be this. What does it mean? So you will find for r equal to 1, you will find that T23 is equal to T32. Okay, T31 equal to T13. T. So in your Cauchy stress, when you are saying that, this is equal to this, these two are equal, these two are equal, and these two are equal, what you are considering? You are considering a balance of angular momentum enforced into your stress tensor. So symmetry of the matrices, symmetry of the stress tensor is coming from where? From the angular momentum balance. So if I go back to your Navier-Stokes equations, if I go back to the Navier-Stokes equations, if I go back to the, sorry, where is the Navier-Stokes equations? If I go back to this equation is balance of what? This equation is a balance of what? This equation is balance of what?
Linear momentum, sir.
Only linear? How come you get this? When you try and get this, what you assume? You assume the Newton's law of viscosity, which is like where is the expression? Which is like this. In this, you say that this is equal to this, right? This is equal to this, right? This is equal to this. Moment you take these to equal, correct? Then you enforce that there is a balance of angular momentum too. If these two are not symmetric, then there is a chance that the angular momentum has not been considered. It is only linear momentum. But moment your stress tensor is symmetric, where you are getting the symmetry of the stress tensor? When you take a moment of your forces, right? And you consider the torque, balance of the torques rather than forces. What you say that rate of change of angular momentum is equal to what? Is the summation of the surface and the body torques. Okay, body force and the surface forces, the torques associated with the body and the surface forces. Moment you do that, what happens? You get your stress tensor to be symmetric. Right? And that is the reason why when you write the stress, when you say that if there is a stress tensor, although there are 1 to 9 terms, you say that there are essentially 6 terms. Why? Because 3 diagonals and all these are symmetric matrices. They're equal. Tau 21 is equal to tau 12. Tau 31 is equal to tau 13. Right? Tau 23 is equal to tau 32. So this combination you get from where? You get from the balance of angular momentum. So Navier-Stokes equations consider both linear as well as angular momentum. Newton's law talks about, when you are using Newton's law with this framework, it consider when you are applying Hooke's law for the force balance, when you are applying Newton's law of viscosity for the force balance, you have already considered linear as well as angular momentum balance. Both. Is that clear? The clarity comes. So I could clarify one thing, how forces are connected to first dynamics is getting through traction. Force is connected to traction to Cauchy stress. So how kinematics and dynamics are bridged. This is number one confusion that we cleared. Number two confusion what we cleared. What are the invariants? What are the eigenvalues? And from there, how the pressure originates? How do we separate out pressure in order to identify the deviatoric part of the stress, which is generally correlated as stress is proportional to strain, right? When you say that stress is nothing but the deviatoric stress, that doesn't have the pressure component. Okay, so Newton's law, Hooke's law, whatever you enforce on the deviatoric stress rather than the thermodynamic pressure. Pressure is an eigenvalue, it's an invariant, it comes out of the Cauchy stress. Okay, the part which doesn't change, with with the variance of with the change in the frame. Correct? Any question up to this point? Any question?
Sir, does it mean that if we have a rotational flow, then the matrix will not be symmetric? I mean, the stress matrix.
Rotational flow means no. You apply. I'm extremely sorry. If we apply the same thing for the rotational flow also, right? We never say that del cross V equal to 0. What is an irrotational flow? In irrotational flow, when it is del cross V equal to 0. This is the signature of an irrotational flow, but nowhere we have said del cross V equal to 0. Isn't it?
Okay, okay, sir.
Rotational flow has nothing to do with this angular momentum balance. Angular momentum balance has to do with how your stress strain correlations are changing with the movement. See, you have to understand that what from where am I coming? When I'm rotating this, see what is this mx, my, and mz? What do you mean by mx, my, and mz?
The moment of the forces.
Correct. So if you just look at the arrow at the top, if you just start rotating with that arrow that is going upward, right? So that is your mz. When you are holding the z-axis and then giving a rotation, right? That is one way of rotating it. When you are putting the y-axis and giving a rotation, that is the way you can rotate in y. When you are taking the x-axis and giving a rotation, that is the way to rotate in the x-axis. Now you say that in a three-dimensional rotational framework system, I give all these moments to all the surface and body forces that are existing there. So I'm considering here rotation and everything is there. It is embedded. But the consequence is that, moment I say that force equal to mass into acceleration, these are the total forces, right? This is the total torque. That what I say that is the torque associated with the mass into acceleration, right? This is where I am enforcing the Newton's second law. Is that clear to you?
Yes,
now,
yes, sir.
when I do that, I get as a result, and then if I take the linear momentum balance equation, which I have already proven, then I get as a consequence, I get my stress tensor to be symmetric. It is the consequence of that. Now, when I write, if I write, say tau is equal to mu into gradient of V or gradient of V transpose, right? Or stress is equal to epsilon into gradient of U and gradient of U transpose, as U is the displacement and E is the elastic modulus. When I write such things, it considers this to be already embedded in this. So it enforces, it has already enforced linear as well as angular momentum balance before considering that. That is already there. Whenever your stress tensor is symmetric, it is coming from your angular momentum balance. Is that clear?
Yes, yes, sir.
Great. Now, say when you really describe, I think this particular slide is a little bit misplaced. I think this should go a little later. No, fine. I think it should be okay. Yeah. So I'm sorry, I was thinking in a different direction. Now, say suppose you have if you have an object which is a rigid body object, and it is a kind of, it's a rectangular rigid object like this, and say suppose you are throwing this object to a certain place, say suppose here, and it is going here, right? This is one type of motion. This type of things are in dynamics called motion, right? So there is no change in volume, there is no change in area, there is no change in volume, there is no change in area. It has just moved from one place to the other place. But this is not the only variety of motion. Say suppose you have an ice cube which is melting. It's an ice cube, same size. Say this is melting. And over a period of time it is becoming water. Okay. This is also a motion. But the difference between this motion and this motion is that in this situation, volume, area, everything is changing. Correct? So in order to take different types of motions, different types of descriptions and references are created so that, the analysis become easier. Right? So let us see what type of descriptions are created. Now, this particular description is called, whatever we are using here in this particular slide, this particular description is called the material description, in which the initial configuration, that is del capital X and del capital Y. This is the initial configuration. This is the del capital X and this is the del capital Y. So suppose this is del capital X and this is del capital Y, right? So initial configuration, whatever we do, whatever calculation we do based on the initial configuration, that is delta X, delta capital X and delta capital Y. Now this type of material description is very much suitable for any solid object which is not changing volume or area. And the boundary is, say, suppose you have a bottle like this, which is incompressible, which retains its geometry and all everything. It is absolutely easy to really handle this in terms of material description. However, say suppose if you have a fluid, the moment you put say suppose you have a glass of water, right? You have glass of water, right? And there is a molecular arrangement associated with this glass of water, right? Molecular arrangement is there. Now we just shake it a little bit. What is the probability that you get the same molecular arrangement once again? Same configuration once again, even inside the glass without losing any mass? What is the probability that you get the same molecular arrangement?
Very low.
Nearly zero, right? So for fluid, there is nothing called a configuration. So for that, what you do, you don't really retain the initial configuration, but you do every analysis based on the final configuration. Okay, so based on that, what you do, you generate a relative description. This relative description is always the present, and present is always defined as the small, right? Which is also called the Eulerian description. And for the rigid bodies, you call the material or referential description, which is also called the Lagrangian description, where you always consider the capital. Capital means capital X means I'm going back to its original configuration. Whereas small x, small tau, capital X, capital T means I'm going back to its original configuration. Whereas the configuration at t equal to 0, that is called a Lagrangian description. Whereas the Eulerian description is that I always analyze in the present at time t equal to t, which is the small x. So these are the two descriptions of motions. How do I define strain? So suppose in the x direction, delta x is original configuration and ux is perhaps you are stretched with a force. So epsilon you define del u by del x. What is the unit of epsilon x? What is the unit of delta ux? जल्दी बताओ बाबा, इतना क्या टाइम ले रहे हो?
Meter per second.
No, here it is displacement. Okay, I'm talking about strain and deformation. You have to always be careful about strain rate and strain. Strain rate means it is velocity. Strain means it is only elastic. Okay, so u here is displacement. Uy, ux is displacement, right? So delta x is initial configuration. You have stretched by delta ux. Delta y is initial configuration. You have stretched by delta y. So what is the unit of ex?
No unit, sir.
It will be dimensionless.
Dimensionless. EY, dimensionless, right? So these are all EX, EY. And EXY, what I say, it is like, say EX, how do I get? I get this configuration, right? So what I say that I first give a stress in this direction, delta U. It first shifts there and it goes that direction there. So it first undergoes a configuration θ1, deformation θ1, then it undergoes another deformation, first in this direction and then second is that direction. And then I average out of θ1 and θ2 half of gamma xy. Okay, which may be, see what is θ1? θ1 will be in the x direction del uy. So del ux, del y. Del uy by del x. Okay. And in the y direction del ux, that is del ux by del y. So half of del ux by del y. So now if you look at the strain components, say if I put a strain matrix like this, which is epsilon x, epsilon yy, epsilon xy. Sorry, this is yx, say epsilon xy, right? If I put a strain matrix, you will find that, this is nothing but del u by del x. Then this is half of del u by del y plus del v by del x. This is again the same thing in this place, and then this is del v by del y, right? So you have 4 components here. Did I use any law here in this particular description? Did I use any law?
No.
So what is this called?
Kinematics.
This is kinematics, right? So I am arriving at the strain tensor. So basically I have written here as a strain tensor. When you write stress is proportional to strain, right? So if stress is a tensor, strain is also a tensor, right? Without using any law, Newton law, Hooke's law, anything, without using any law, just taking rectangles and looking at their movements and creating situations, I can really go for a kinematic analysis to get the components which are associated with, this only when you have displacement, it will be Hooke's law. When you have, this strain will become strain rate. I will immediately show you strain will become strain rate. That will become the Newton's law of viscosity. 1 minute, huh? Sorry, that was an important phone call I had to take. So the interesting part you can understand, I'm audible, right, to all of you? Hello.
Yes, sir.
Yeah. So interesting part to think that, these terms like, del U by del X, del V by del Y, these sort of terms, we can just straight away get from the geometry and stress and say, suppose what is this? This is del U by del X. That means in the X direction, what is the displacement? What is del U by del Y? In the Y direction, what is the del V by del Y? This will be del V by del Y. If V is the displacement in the Y direction, what is the in the axial? This is a kind of, these are called the uniaxial extension, right? The uniaxial, the direction in which the coordinate is there, what is the change? The direction which is there, what is the change? Now, this is the tangential component coming in Y. In the X direction, how much has gone this side? So first, what I start with this box, and then what I do, I push it, shear it like this, right? So it goes in that direction. Then what I do, I shear it in this direction. So then you will find like, the thing will come like this. So this shape will come up. Let me draw once again. I think I have moved up this one. So it will happen very easily. So, say you have a coordinate system like this. Initially you had like that, right? So in that, first what you do, you first stretch it to this direction like this, right? So, your things become like that. This is your first step. So in the X you have sheared, right? And then you have done it in the Y. So it goes like that, it goes like that, and then it goes like that, right? So in that process, you will find like, this shape will come out. This shape will come out. In this process, the shape will come out. So what I'm trying to say, first I give a shear in this direction, then I give a shear in that direction in order to get like, θ1 and θ2. And if I take an average of that, I end up getting this. So you can see that, say, suppose PQ is the initial. Now I'm generalizing the whole thing. If PQ is my object, and after some point of time, P has gone to this P, capital P, you see, capital P is my initial configuration, and small q is my final configuration. So capital P has gone to small p, capital Q has gone to small q. Now you see it's a full generalization, right? Where ds is the initial shape. So what is the motion? Motion du is what? UQ plus NP. So UQ plus UP. UP is this, and UQ is this. So you can see that this is the U vector, this is the P vector. UQ minus UP leads to the motion, right? And as S tends to 0, that means, you are trying to go for a. So suppose what is dux by ds? So by chain rule, dux by dx, dx by ds, dux by dy, dy by ds. Basically, you are going for du. U is a function of x and y, and then dividing by s. Now, if you do that, you get dux by ds, dux by dy. So ds is the initial configuration. Dux by ds is the ux is what? Dux is the direction, strain in the x direction. Dy is the strain in the y direction. Dx, ds, dy, ds are the coordinates. Now you see the straight away the strain tensor comes like ux, dx. These are the diagonals. Dux, dy. These are the normal terms. These are the shear terms. Now, if you really focus this, you can express this as a combination of, say, if you have, these are the 4 components of strains, you can express this in terms of what? Diagonal remains same, this remains 0, and this you can do as plus average of these two, symmetric, and minus of these two. Correct? Now this is nothing but so this J, the total J, which is the Jacobian matrix, which is the transformational matrix from here to here. So that becomes what? E is the Eulerian stress tensor, which is the translation part, and sigma. Okay. This is sigma or omega. This is omega, right? So omega is the rotation part. So this you will find that this will become curled, and this will become the translation. This is the linear translation, and this is the rotational part, right? So any motion has a normal and shear, and in the normal and shear total altogether can be expressed in terms of the translation and rotation. So any motion, by simple geometrical argument, you can see that, they can be they can be different. They can be represented as this. Now, if you put it in a 3-dimension, you will find 3-dimension. It will look like this. So this is the diagonal component. These are the tangential components, and this is the tangential component. This is basically skew symmetric matrix, and this is a symmetric matrix. If you add these two, what you get? You will get, the strain tensor, the Eulerian strain tensor. Now, this can be written as this. This is nothing but, the curl vector that we were discussing about. So in tensor notation, E is like, you can now see that from where E is, this is written in a bit different format, gradient of U plus gradient of U transpose, right? So here it is written as sigma is what? Half of what? This is half of what? Half of gradient of U minus gradient of U transpose, right? So these two, if you add, so any motion that is happening, it's nothing but any displacement that is happening from kinematics without getting into any other argument, just from kinematics, geometrical arguments and mathematical arguments, you can really say that a displacement is nothing but a translation plus rotation. Rotation can be zero, translation can be zero, displacement can be only rotation, displacement can be only translation, right? And displacement can be a combination of that. You can fundamentally obtain. Just to complete the whole thing, the same is the argument for the fluid. So this is a translation, this is a rotation, this is an angular deformation, this is a linear deformation. Okay, just check that. Say suppose there is a motion, right? There is a motion. There is an object which is suppose AB, right? And then you try to define. Let me just look at the deformation first. Then we'll go for the. Then we'll go for the. Let us look at the angular deformation first. Then we'll go for the rotational motion. What is an angular motion? Angular deformation motion. What we have defined. Say suppose this is my delta x. This is my delta y. And then, how do I obtain this? You see that first, what I did, I deformed it by half of delta alpha plus delta beta in this direction, right? And then I brought it back half of delta alpha plus delta beta. Just remember this. We go back here, say suppose there is a motion that is taking place. This has become this, which is an arbitrary. Say this AB was there, it has become a rectangle like this, which is an arbitrary. In Y direction, the deformation, we can say delta eta. In X direction, we can say this is to be the delta zeta. Now, I say that this is again a combination of this rotation, that is half of delta alpha minus delta beta. And this deformation this is nothing but half of delta alpha plus delta beta. Now, what is half of delta alpha minus delta beta? What is delta alpha? Delta alpha is what? Delta eta by delta x. And what is delta beta? Delta zeta by delta y. Now, what is delta eta? In y direction, del v by del x. Basically, it is del v into delta t. Del v into delta t. That means change in the velocity with respect to the change in time. So you can write it del v by del x by del x into delta t. This part, delta eta by del x. Similarly, you can write delta zeta by del y, del u by del y by del y, and delta t. So if this cancels out, so essentially this notation comes out to be what? Half of del v by del x minus del u by del y. So when you take a curl, say suppose when you are taking the curl of v, okay, when you are taking del cross v, what you are doing? You are basically having I, j, k, three determinants, del x, del y, del z, and then you have u, v, sorry. You have u, v, and w, right? So if you just take the I part, so what you will get? Del w by del y minus del v by del z, right? When you take the j part, you get what? You get del u by del z minus del w by del x, right? And then when you get the K part, what you get? You get del V by del X minus del U by del Y, right? So here you see that del V by del X minus del U by del Y. That means you have got the K components, that is omega Z. So just simply considering these kinematic arguments that this particular thing has gone to this. It's a combination of a rotation and it's a combination of a deformation. Rotation amounts to be half of delta alpha minus delta beta. So delta alpha is this and delta beta is this. So I'm just considering what? Half of delta alpha minus delta beta plus half of delta alpha plus delta beta. If I just, create combinations like this, plus and minus, then what happens? I get like, what is my motion here? This is delta alpha. What is my motion here? Delta beta. It's a combination of these two events. One is the rotation here and the one is the deformation here. If I just, arrange all the terms associated with that related to this motion, say suppose delta alpha minus delta beta, I get omega x, omega z, omega x, and omega y from the geometrical arguments, which can be defined as omega. Omega is nothing but half of this. This is called the vorticity. This is called the curl. By the way, curl is what? Curl is twice of vorticity. Okay, so this is curl. Del cross V is curl. Omega is the vorticity. So curl is the twice of the vorticities. From symmetrical geometric arguments, we get the rotation and we get the deformation. So any motion, linear motion, is nothing but a combination of rotation and deformation. Right? Anyways, this last part is a little bit like, I know it's on a jittery ground. So we are going to really work on this in the next lecture on Friday. And then we are going to take up from there. Okay, any question up to this point? No questions. Great. Okay, so we meet on Friday. Yeah, somebody wants to ask question. Shubham.
No, sir, I was just saying it's fine now. We need to look at it again too.